In this video, we're going to take a brief look at a schematic editor and circuit emulator called MicroCap11. As we'll see, the simulator can do both AC and DC analysis as well as transient analysis. It can also do some other things that we won't consider, such as distortion analysis, worst case analysis, and stability analysis. There is a demo or student version that is free with a limited set of capabilities, and there is a full capability professional version that costs $4,500. We're using the demo version in this video. To get the demo version, you need to fill out this request form, and they will give you a download link by email. The current version 11 is compatible with Windows XP, Vista, and Windows version 7, 8, and 10. There are two extensive PDF manuals available for downloading, a user guide and a reference guide. Okay, let's open MicroCap and take a look at the user interface. First, we'll explore the list of components we can use in our circuits. We open the list of analog primitives and then the sublist of passive components. There are resistors, capacitors, inductors, diodes, transmission lines, Zener diodes, transformers, and more. Notice that when each type of component is highlighted, its schematic symbol is shown in the upper box. Some components are only available in the professional version. Shifting to the active components, we see NPN and PNP bipolar transistors, NMOS and PMOS FETs, depletion mode FETs, operational amplifiers, and even gallium arsenide FETs. If we look at active sources, we see batteries, voltage sources, sine wave sources, and pulse sources. There are two connectors we should be aware of. First is a ground, and the second is called a tie. The tie is useful when we want the same signal to appear several different places in a schematic. There are some special purpose components available also. There is a voltage-controlled switch, which causes a switch to open or close depending on the voltage across the two control pins. There is also an analog library where there is a collection of specific components. For example, there is a 2N3055 transistor in the power category. Many of these specific semiconductor devices are only available in the professional version, but a number are available in this demonstration version. There are even some vacuum tubes in the list, such as a 6L6 pentode and a 12AX7 triode. We can find a variety of logic gates in the digital primitives section, and we'll find specific TTL logic parts in the digital library, such as a 7402 2-input NOR gate or a 74120 dual pulse synchronizer. There is another menu along the top of the window that facilitates entering the more common components into a schematic diagram. The first one is a ground. Just click on the ground symbol and drag it into the center of the window. Let's zoom in so we can see it a little better. To move anything in the schematic, you must be in the select mode. To activate the select mode after placing a component in the schematic, you can hit the escape key, click on the select mode button in the upper left portion of the tools bar, or simply press the space bar on the keyboard. Now let's place a resistor on the schematic. When the mouse button is released, a window opens allowing us to pick a part identifier such as R1 and the resistor value such as 50 ohms. Standard engineering notation is used to express numbers. For example, 2700 could be written as 2.7K. The K can be either upper or lower case, with no blank spaces being allowed between the number and the letter. The letter M will mean milli, U would be used for micro, N for nano, and P for pico. MEG or meg is used for mega, G for giga, and finally T is used for tera. You can also use exponential notation so that 4.2n equals 4.2 e to the minus 9. Next we'll add a capacitor, and it will be called C1, and let's give it a value of 0.15 U or 0.15 microfarads. Now we'll add an inductor called L1, and we'll assign a value of 1.0 M or 1 millihenry. Components can be rotated several ways. First, click on the object and hold the left mouse button down, then click on the right mouse button. Each click rotates the part 90 degrees. Control plus R on the keyboard also rotates the selected object. Lastly, there's a button in the upper toolbar that rotates the object. There are also buttons in the toolbar to reflect the object up or down and left or right. If you're in the select mode, you can move the part identifier or the value independently from the component itself. If you pick a component like a diode, you can use the pull-down menu on the right-hand side to choose a model like the 1N4001. If you check the Show box at the top, the model will be shown on the schematic. Now we'll place a transistor on the schematic. Select the model as a 2N2222 and reflect it right to left. Next we'll place an N-channel 2N6660 MOSFET transistor and an LM741 operational amplifier. And last but not least, we'll place a 12-volt battery. I think we're ready to set up our first simple but functional circuit, an RC low-pass filter. We'll start out by going to the File menu and selecting a new schematic. Next, we go to the Component panel, open the Waveform Sources list, and select a pulse source. After dropping it on the empty schematic window, a smaller window opens, allowing us to choose a model. We select Pulse and click on the Show checkbox so the model type will be displayed on the schematic. Now we have to pick some parameters for the pulse source in the lower part of the window. P1 is the time delay to the leading edge of the pulse. We'll accept the default of 100 nanoseconds. P2 is the time delay to the 1 level, and once again we'll take the default of 110 nanoseconds. This defines the rising edge of the pulse. P3 is the time delay to the trailing edge, and we'll set this to 500 microseconds, or a half a millisecond. P4 is the time to the 0 level, which we choose to be 510 microseconds. This defines the trailing edge of the pulse. P5 is the repetition period, which will be 2 milliseconds. The default value for V1 is 5 volts, and V0 is 0 volts. Next, we click on the OK button. We'll place a resistor named R1, give it a value of 1.1 k ohms. Rotate it by 90 degrees and move it closer to the pulse source. Let's zoom in a little so we can see things a little better. Now comes a capacitor C1 with a value of 0.15 microfarads. The final components are 2 ground symbols. Now let's connect these circuit components. Click on the Wire Mode button in the toolbar, and it will let us connect the various ends of the symbols. Next, select the Grid Text button in the toolbar. This will let us identify different nodes in the circuit with alphanumerics. We'll mark 2 nodes as in and out. We can now navigate to the Analysis menu and select Transient. A limit window opens for us to select some parameters. Each line in the lower part of the window represents a curve that will be generated in the analysis. First, we'll choose the maximum time range of 10 milliseconds. Next, we'll set the p-value of the second curve to 2, which will generate 2 separate curves instead of 2 curves on the same graph. Note the x expression for both graphs is a t, which stands for time, and the 2 expressions for the y-coordinate are v in, or the voltage at the in node, and v out, or the voltage at the out node. Thus we'll get 2 graphs showing the input from the pulse source and the output voltage from the RC circuit plotted against time. We click in the Auto Scale Ranges box so MicroCap will pick the ranges in the 2 graphs for us. To see the analysis, we push the Run button. So here are the 2 graphs, and on the top we see the voltage produced by the pulse source. Note the amplitude is 5 volts, which was the default value for V1 that we saw earlier. And the period of the pulses is the 2 milliseconds we chose. The bottom graph shows the output voltage, which grows exponentially from 0 towards 5 volts and then decays back to 0 volts at the end of each pulse. Let's take a quick look at the AC analysis of the same RC circuit. First, we'll have to switch from a pulsed source to an AC source, so let's go to the component panel and select the sine source. We'll choose the general model and take the default amplitude of 1 volt. We don't have to worry about the frequency because we'll be sweeping the frequency in the AC analysis. Click OK and go to the Analysis menu. After selecting AC Analysis, a window opens. Let's look at the settings. The frequency range is set from 200 Hz to 200,000 Hz with a logarithmic scale. The P settings will give 2 graphs with the x-coordinate set to frequency. The y-coordinate of the first graph will show the ratio of the output voltage to the input voltage in decibels, and the y-coordinate of the second graph will show the phase of the amplitude ratio. The Auto Scale Ranges box is checked, so MicroCap will scale everything for us. Now click on the Run button. Here are the 2 graphs. In the top curve, we see that the output decreases with frequency, which, of course, is what we expect from a low-pass filter. The cutoff frequency is defined to be the frequency where the power ratio is 1/2, or -3 dB. And in this case is 964 Hz. At this same frequency of 964 Hz, the phase of the ratio of output to input is -45 degrees. Here's another circuit that can be described as a Wien bridge amplifier. We'll use AC analysis to see how large the gain is. It uses an LM741 operational amplifier, which is one of those specific components available in the evaluation or demo version of MicroCap 11. Notice we've labeled the in and out nodes, and we've used the tie connector mentioned earlier in the video. The tie connector connects the plus and minus voltage sources to the power supply pins on the operational amplifier. The input signal is supplied by a sine voltage source. Note that if you click on the Node button in the toolbar, node numbers appear on the schematic. These node numbers are useful in identifying voltages and currents that you would like to plot using the various analyses available in the MicroCap 11. Although it is not explicitly shown, the node number of the ground connections is always 0. Now we go to the menu bar and select the AC analysis, and the Limits window opens. The frequency range is set from 5 to 50 kHz, and we are asking for just one curve showing the ratio of the output voltage to the input voltage expressed in decibels. Once again, the Auto Scale Ranges is checked. We click on the Run button and the graph appears. It has a definite peak at one frequency. Microcap will help us mark the frequency and the gain of the peak by using the Tab Mode button. This shows the peak gain is 67.48 dB at a frequency of 12.5 kHz. There is one other button we can use to identify the peak of the curve. It is called the Global High button, and once again this shows the maximum gain at 12.5 kHz. We just looked at an amplifier with a peak response. Now let's look at one with a notch response. Once again, the tie connectors are used to make the schematic a little easier to understand, and we have labeled the in and out nodes in the circuit. Let's go straight to the Analysis menu and select AC. By now, the limit windows should look familiar. In this case, the frequency range is between 10 and 500 Hz, and the scaling is set to auto. This means Microcap will choose between a linear or a logarithmic scale. We've chosen a single graph in this case that will show the circuit gain, or the ratio of the output voltage to the input voltage in decibels. The Auto Scales Ranges is checked. Here's the curve showing a very sharp notch at one frequency. Once again, we'll use the Tab Mode button to show the frequency and attenuation of the notch, which is minus 60.8 decibels at 59 Hz. I think these AC analysis curves make it very easy to understand what these circuits do. The next example is a circuit intended to operate a relay that controls the fan for a VHF repeater. The control signal comes from a CAT 300 repeater controller, and we will use a ULN 2803 Darlington transistor array. The ULN 2803 device is not available in Microcap, so we will recreate the schematic for one of the NPN Darlington transistor pairs. This in turn drives a 2N3904, which has a relay in its collector circuit, and the relay switches 12 volts to run the fan. The amplitude for V1 and V0 in the pulse source are set for 3.3 volts and 0.7 volts respectively to account for the worst case expected from the CAT 300 controller. The parameters for the relay are chosen to represent the actual relay being used. The coil resistance is 720 ohms. The coil inductance is 150 millihenries. The contact resistance in the on state is set to a very high value because this model is for a normally closed relay, but we can simulate a normally open relay just by switching the sense of these resistances. So we'll complete this switch by setting the off resistance to 10 milliohms. The current that guarantees the relay will operate is set to 12 milliamps, and the minimum current required to hold the relay on is set to 5 milliamps. We now run the transient analysis. Look at the curves at the bottom of the limit window. The top curve will show the pulse source. The second and third curves will show the base current and the collector current for Q3, the 2N3904 NPN transistor. Finally, the last curve will show the voltage that will be delivered to the fan. Well, we can look at the bottom curve and see that the relay did not operate as anticipated. Curve 3 shows us why. The 2N3904 NPN transistor did not shut off sufficiently to disable the relay, so we'll need to make a change to the circuit. There are probably several possible changes that we could make, but let's try adding a forward bias diode D4 to the emitter of Q3. This diode will have a small voltage across it that is more or less independent of the current passing through it. This will increase both the base and emitter voltages on the transistor Q3. And this should help the ULN2803 Darlington pair turn off Q3 and release the relay. Let's rerun the transient analysis. We've had to make one small change to the bottom curve since adding the diode changed the node number of the relay switch from 8 to 9. Now the lowest curve shows that the relay is indeed being turned off and on as the pulse source switches. As predicted, the second and third curves show that Q3 is being sufficiently turned off to disable the relay. This example shows how a circuit emulator like MicroCap can help tweak a design and perhaps save a lot of time experimenting with hardware changes. For the last example, let's take a look at a diplexer. Diplexers are commonly used when you have a dual band VHF and UHF antenna, but two separate radios. Sometimes these are called combiners or separators, but they are comprised of a low-pass filter and a high-pass filter connected together at a common port. A diplexer implies operation at two frequencies on different bands. This one is for the 2 meter and 70 centimeter bands. It's easy to spot the low-pass filter because the series inductors will still have some response at DC. The sine source is fed through a 50 ohm resistor, R1, at a common node marked 2 in the schematic. Resistors R2 and R3 are 50 ohm loads, and the diplexer is designed for 50 ohms. So let's start the AC analysis. To begin with, we'll plot the 2 meter and 70 centimeter outputs on the same graph expressed in decibels. In this case, we've already set the scales for the y-axis. The blue curve is the low-pass filter, and the red curve is the high-pass filter. The insertion loss is about minus 0.1 dB at 144 MHz and 440 MHz. The high-pass filter has about 53 dB of loss or isolation in the region of 144 MHz, and the low-pass filter has a loss or isolation of 52 dB at approximately 440 MHz. We should remember that the inductors and capacitors are ideal components without any losses and represent a best case. Now, back to the limits window, and we'll add two more curves. This curve is the return loss in decibels and is calculated from the magnitude of the reflection coefficient. We calculate Z sub L as the voltage at node 2 divided by the current flowing through R1. The last curve is the voltage standing wave ratio, which can be calculated from the reflection coefficient. Now we'll hit the run button and look at the curves. Once again, the middle curve is the return loss, which is about 38 dB at both 140 MHz and 440 MHz. The voltage standing wave ratio is close to 1.02 at both frequencies. We're going to look at one last circuit to see one feature in the AC analysis bag of tricks. This is from a Cantronics KPC 9612 packet TNC and provides an amplitude boost to the higher of the two frequencies used in packet radio transmissions. The key thing to notice here is this 10K potentiometer labeled X3. A potentiometer is implemented by a so-called macro in MicroCap 11, which is explained in the reference manual. The in and out nodes are labeled as we've seen several times before, so let's go quickly to the AC analysis limits window. Notice the stepping button at the top. This opens the stepping window with a number of tabs. We select X3.R1 from the Step What pull-down menu, which is the value of the potentiometer resistance not shorted out by the wiper. We will determine this value is to start from 0 to 10K ohms in steps of 2.5K. Step It is set to yes using a linear method. and the step variables in nested loops is selected. Say OK, reopen the limits window, and hit the Run button. Now we see a family of curves generated by the circuit when the potentiometer X3 is stepped through values from 0 to 10K. So let's summarize what we've seen. MicroCap 11 has a schematic capture capability using almost all of the generic electronic components and has a library of specific components. There is a demo or evaluation version that is free and may be downloaded from the internet. Many of the specific components are only available in the professional version, but the demo version has many of the more common components. After entering a circuit schematic, one may then use several analytical tools to investigate the circuit properties. We have explored the transient and AC analyses in this video. There are comprehensive user and reference manuals available online, and to help the user become familiar with many of MicroCap's features, the program offers a number of sample circuits. Here are some of the sample circuits. A ring counter oscillator, a step-up switching regulator, a MOSFET mixer, a switching capacitor bandpass filter, and for the old timers, a vacuum tube amplifier. So if you're working on a do-it-yourself project or just wondering if a small circuit could solve a ham radio problem, think about downloading MicroCap 11 and do some electronic exploring.